Okay. Hello, everyone. Very warm welcome to the NZ Knowledge Series. We're coming back in November with a little short break in October. I hope you all had a great Diwali vacation and you are also back to your work and other things with, refreshed from the break that you've had. So the NZ Knowledge Series is a platform that brings industry experts to showcase their projects, products, technology, policy, ideas, and everything about building energy efficiency to grow engagements for net zero energy buildings in India. This initiative is supported by the MAITRI program, which stands for Market Integration and Transformation for Energy Efficiency, supported by USAID. You can learn more about the program on our website, maitri.edsglobal.com. A little bit about myself. I'm Deepa. I'm an architect and a green building consultant, and I will be the session moderator today. So today we are going to discuss vapor absorption technology. This is a kind of a cooling solution for various applications, including comfort cooling. This system uses a heat source to run the process, unlike electricity used by compression chillers. When waste heat, steam, or solar power heat is available, it presents a potential to be independent of the grid. Using water as refrigerant, it provides an environment-friendly alternative to provide cooling. Discussing this in depth is our speaker, expert speaker for the day, Mr. Vaidyanathan. He's joining us from Chennai, from Thermax Ltd. He is a product manager for absorption cooling business at Thermax Ltd. He has been associated with Thermax Ltd for over 15 years and has extensive experience in design, testing, marketing, selling, and even troubleshooting of absorption chillers. He is a mechanical engineer by education and also has a postgraduate diploma in management. I welcome you, Mr. Vaidyanathan, on this webinar, and we look forward to a great session from you. Mr. Vaidyanathan, please unmute yourself and you can present from this point on.
Thank you, Deepa. Good afternoon, everyone. Before getting on to session, so I will just brief you about what are the deliverables, what we can look at from this session. Primarily, we will try to understand what is absorption technology, how it can help each one of you in your core sectors, how you can utilize them and generate green cooling. And what are the different avenues of using this in commercial establishments and how it works, etc., followed by some case studies. Brief introduction about my organization, Thermax Ltd. And we are from the absorption cooling and heating background of Thermax. We have over 30 years of expertise in absorption cooling technology. We cater to various industries, various applications, wherein we do a lot of solutions based on waste heat recovery. We have over 6,000 installations across the globe, and most of them are in the realm of trigeneration. We have over 100 plus applications in which we have established our product as a solution for achieving green cooling. So as the slide mentions, we can cater to applications starting from -40 degrees Celsius to plus 180 degrees Celsius using the absorption technology. So we have this manufacturing facility, which is one of the IGBC Green Building certified facilities for in the manufacturing sector. We have got a platinum rating for this factory, and it is a automated and digitized manufacturing facility where we can make chillers up to a capacity of 3000 TR, and we also can do the performance testing of it. Yeah. To start with, we'll try to understand what are the different solutions one has for refrigeration, for achieving refrigeration. So the most predominant or most widely used system is the vapor compression system, wherein there is a refrigerant which is compressed by a mechanical means, by using a screw compressor or a centrifugal compressor or a reciprocating compressor. So these are the three prominent technologies, though there may be different other types of compressor technologies, wherein the centrifugal technology caters to the large capacity applications, which are maybe 300 TR and above. The smaller applications are catered to by screw chillers, maybe up from 25 TR onwards, and maybe special application, niche applications for negative temperatures are catered to by the reciprocating technology. So what we are going to see today is an alternative technology to this vapor compression technology, which goes by the name vapor absorption technology. Under this technology, there are two types of systems. The focus of this session is going to be on the lithium bromide water absorption systems, which are nothing but skid mounted packaged units, which can run with a variety of heat sources to achieve positive as well as negative cooling. And there is another variety, water ammonia system, which is predominantly used for sub-zero temperatures, maybe temperatures up to -30, -40 degrees Celsius. Now, a brief introduction of this technology. Many of you would be interested or would be surprised to know that this is one of the oldest of the refrigeration technologies. Its origin predates the compression technology. It originated in the North American region. Maybe in the early 20th century, this technology got a wide popularity much before the electrical chillers came into existence. Later on, post the World War II, this was taken over by the Japanese, because Japan was devastated by the Second World War and they wanted to rebuild the country. And since they were not having enough energy in their country, they had to import it. So they wanted to find a technology which can optimize the use of energy. That is where a lot of research and development happened in the 60s and 70s. And Japan became one of the global forces in this particular technology. Today, it is predominantly used in almost all the large developed countries as well as developing countries as a means for achieving maybe cooling in industries as well as in commercial complexes. Now, the significance of this technology comes from the fact that it is a thermally activated technology, which means that this equipment is run not by electricity but by heat. Heat can be in various forms, as you can see. It can be driven by steam, it can be driven by hot water, by exhaust gases from an engine or a turbine or a furnace, or it can be driven by thermic fluid, which is available in the industries. Or if nothing is available, at least it can be run with the help of a fuel like natural gas or diesel or LPG. And since there are customized possibilities available, it can be tailor-made to operate on one or more heat sources as well. So these are called as the multi-energy absorption chillers. So any chiller will have something called as a refrigerant, which is going to be the driver, or which is going to drive this particular equipment. So in the case of an absorption chiller, the refrigerant is a natural refrigerant, and it is nothing but pure water or DM water, demineralized water is used as the refrigerant. Unlike the electrical chillers where you have mechanical drives, like you will have an electric motor or an engine which is driving the compressor, here it is entirely driven by heat, and the heat is used to recharge or reactivate the absorbent, which is a salt solution called as the lithium bromide solution. It has properties similar to sodium chloride, which is common salt. The salt solution is working along with the natural refrigerant, which is water, to deliver the cooling needed for the application. Moving forward, so as mentioned in the previous slide, you can see that there are various heat sources which can make this equipment run. Maybe exhaust gases with temperatures over 250 degrees Celsius, hot water with temperatures 75 and above, steam starting from atmospheric pressure, that is waste heat in the form of vapor, flash steam. They can also drive an absorption chiller, or as I mentioned, natural gas or oil can be used as heat sources. Now it's the utility or the output delivered by the absorption unit can be in various forms. Predominantly, we know this technology as an absorption chiller delivering cooling. But this technology also has a potential of delivering chilled water, hot water, or a combination of chilled water and hot water, which can be used for space heating as well as space cooling around the year, where you have heating delivered during the winter months and cooling delivered throughout the summer. Now, why one should look at absorption chiller technology? The first and foremost factor is low operating cost. In most of the cases, absorption chillers are run on waste heat. So since the heat source or the driving mechanism is a waste heat, so the cost associated to operation is negligible. So because of which this becomes a most viable solution for the user. Since there are no moving parts, this technology also comes with very low maintenance. The second important factor is that we are using an environment-friendly refrigerant, which is water. Unlike the other refrigerant, the CFCs or the HCFCs or the other synthetic refrigerants, this refrigerant doesn't pose any kind of harm to the environment. So it has a ozone depletion potential of 0 and a global warming potential of 0, which makes it the most ideal refrigerant for achieving the cooling needs. Another important aspect is that this can make the users less dependent on the grid, because the power consumption of these absorption chillers are around 90 to 95% lower than conventional electrical chillers. So which means that you can slash your installed capacity or your connected load substantially. This is because in any building, predominantly you can see around 30 to 40% of the entire power consumption is used for driving the compressor. So the air conditioning system and the compressor literally caters to or literally takes away 60% of the power consumed by the building, of which around 30 to 40% is for the compressor. So if you can cut down on that, there can be a huge saving for the users. And the most interesting aspect is that waste heat in various forms can be used to drive this absorption chiller. Now we will try to understand how this chiller works. For this, we have to start with the evaporator, wherein we have a refrigerant, which is the DM water, which will be used to remove heat from the processed water. So from your air conditioning systems, chilled water would be circulated through the evaporator tubes, and the refrigerant would be sprayed on it, which will then pick up the heat from the chilled water and cool it to the required temperatures. Now the heat gained by the refrigerant will be used to convert it from liquid phase to vapor phase. The refrigerant will boil out and we will have refrigerant vapor getting accumulated inside the evaporator. Now, for those of you who are new to this technology, you should understand that this entire operation happens under vacuum. Why it is vacuum? Because we are using water as refrigerant. You might know water boils at 100 degrees Celsius at sea level. As you go to higher and higher pressures, the boiling point increases. And similarly, when you go to lower and lower pressures, the boiling point decreases. So this is the fact that we are utilizing in this absorption chiller. So when you maintain a very low pressure inside the absorption chiller, we can evaporate water at as low as 3 to 4 degrees Celsius. When you can evaporate water at 3 to 4 degrees Celsius, you can cool the chilled water to a temperature which is close to 5 to 7 degrees Celsius. Now, the chilled water getting cooled in the evaporator of the absorption chiller can be taken to various applications. It can be process cooling, it can be air conditioning, it can be for various cooling requirements. Now, as we have seen, we have generated the refrigerant vapor. And since we are operating under vacuum, the vapor, when it gets generated, it increases the pressure, increases the vacuum level. So we have to maintain vacuum levels constant so that this refrigerant can evaporate at constant temperatures, delivering chilled water. So the second process, the second part of the slide, you can see there is a chamber adjacent to the evaporator, which is called as the absorber. Now this absorber duty is to absorb the refrigerant vapor which is getting generated in the evaporator, thereby maintaining the constant vacuum or the constant pressure inside the chiller. So this is achieved by spraying the concentrated lithium bromide solution in the absorber section. Like any other salt solution, lithium bromide salt also has a very high hygroscopic property. Hygroscopic meaning it has an affinity or it has a capability to absorb water vapor. When this water vapor is getting absorbed, there is a heat of dilution which gets generated, which is dissipated to the cooling tower water, which is circulating through the absorber tubes. At the end of the absorption process, after absorbing the refrigerant vapor which has been generated in the evaporator, the concentrated solution of lithium bromide becomes dilute. It gets collected at the bottom of the absorber. Now the next step is to regenerate the concentrated solution and regenerate the refrigerant. So to continue this process in a cyclic manner, we go to step number 3, which is to regenerate the refrigerant. So we take this dilute solution from the absorber, we pump it into the next section called as the generator. In the generator, we use the heat source that we discussed in the beginning. A waste heat source or a live heat source is used to boil the lithium bromide solution, and we will be separating the refrigerant vapor out of it. Once the refrigerant vapor gets separated after boiling out, what gets left behind is the concentrated lithium bromide solution, which can be taken back into the absorber section for further cyclic activity. Now, the refrigerant vapor so separated in the generator moves to the 4th stage, which is called as the condensation. So that is where we have the cooling water circulating through the tubes of the condenser, and the refrigerant vapor which are coming in contact with this cooling water tubes gets condensed instantaneously, and this refrigerant is taken back into the evaporator for further activity. So as you can see, we started with the evaporator where the refrigerant evaporated, it got absorbed in the absorber, it got separated in the generator, and finally it got condensed in the condenser before it comes back, before it goes back into the evaporator section. So this is how it happens in a cyclic manner. we would be going through this important technologies which are relevant for cooling and heating in buildings or commercial establishments. So we have 4 products which are apt for this segment. The first and foremost is the hot water driven absorption chiller. Second is the direct fired absorption chiller. Third is the exhaust gas driven absorption chiller. And fourth is the multi energy absorption chiller. So before moving on to the details of each of these absorption chillers, we can try to understand a small comparison between the electrical chiller and absorption chiller in terms of its efficiencies. In chiller technologies, we call this as the COP, or the coefficient of performance. It is nothing but a measure of how well the energy that is used to drive the equipment is getting utilized. So it is a ratio of the cooling produced upon the energy that is used to drive it. So in case of an electrical chiller, we will normally find that the COP is close to 5. Whereas in case of an absorption chiller, it varies from 0.8 to 1.8. So a layman can get confused, wherein he may wonder why there is a technology which is electrical chiller, which has a COP of 5, and an alternate technology, the absorption technology, has such a low COP, and why would somebody need to go and look at the low COP technologies. So one point which needs to be kept in mind is that COP is a term indicating the efficiency of the equipment, not of the entire system, or it doesn't take into consideration the source of energy. So everything has to be taken to the source of energy to arrive at a meaningful comparison. So when you compare that way, the COP of an electrical chiller roughly works out to be 1.3, vis-a-vis the COP of a direct fired absorption chiller, which is close to 1.5. So which means that an absorption chiller is better, or at least equivalent to an electrical chiller in terms of the COP, the net COP. So we can see this in a graphical representation. So we start with an electrical chiller which has a COP of 5. Now this electricity is delivered from the grid, and the power plant is located in some place which is hundreds or thousands of kilometers away. So it has to be transmitted from the power plant before it reaches the user, which is probably the user may be in a city. So as you can see, in a country like India, the kind of losses that one can see in transmission and distribution, the total loss would be nothing less than 20 to 25%. So to take care of this, the energy that has to be produced, or the power that has to be produced in the power plant, has to be higher than this. So again, in the power plant, there are equipments like the alternator. Again, there is a turbine which will be generating this power, and there is a boiler which generates the steam which is required to run this turbine. So when you take it to the root of this energy production, even with a COP of 5, when you start with 0.64 kilowatt of power per TR of cooling, what we end up is at a number which is much higher than what we started with, which means that we need to burn coal equivalent of 2.34 kilowatt per TR so that the user at the electrical chiller level gets 0.64 kilowatt per TR. So that much is the loss when it passes through all these phases. So what this means is that even though the electrical chiller is highly efficient, the energy required to drive the electrical chiller is much higher than that is required for an absorption chiller. So generally this point gets missed out, and we just compare the equipment efficiency and we get satisfied with at that level. So what we are going to discuss is about a more efficient system, which is nothing but a system which can take care of both these problems. That is, one is the cooling requirement as well as the power requirement in one go, and which can be a source of green power as well as green cooling compared to the coal-fired power plants, which are driving most of the countries across the globe. So it is called as a combined heating, power and cooling system. Its abbreviation is CHPP, combined heat, power and cooling. So what is the relevance of the system in today's world? We'll touch base upon that. So as I mentioned earlier, 50 to 60% of the power consumption of any commercial establishment is for running the air conditioning system, of which around 30 to 40% at any given date is used for running the compressor. So in a CHPC system, what we do is, instead of having a distributed power generation model, or a centralized power generation model, we are looking at a distributed power generation model, where the user will be generating the power required by him using a gas engine, and the waste heat from that gas engine can be used to generate cooling and heating, which can take care of the cooling and heating requirements of the commercial establishment. So the advantage is that the overall efficiency of a CHPC kind of system, that is a combined heating, cooling and power system, can be in excess of 80%. 80% is a bare minimum efficiency of such a system. It can go as high as 90-95% as well. There are district heating systems based on CHP, which generate a net thermal efficiency of 104%. So we will be restricting our discussion to the CHP system, where we are looking at predominantly cooling, because we are looking at geographies which are requiring more of cooling and less of heating. So this chart talks about the system efficiency of a engine-based power generation unit with heat recovery and without heat recovery. So a typical gas engine efficiency would be to the tune of 40%. That means that 40% of the energy from the fuel is converted into electricity, whereas 60% of the energy is getting dissipated, or it is rejected into the atmosphere as waste. Now, when we have an engine, we have two predominant forms of waste heat. One is the exhaust gas coming from the engine, and second is the jacket water or the coolant water, which is used to keep the cylinders cool. So this jacket water and exhaust, if we recover with the help of an absorption chiller, the overall system efficiency can go up from 40% to even in excess of 80%. So the net heat rejection to the atmosphere will reduce to that extent, and whatever is the waste heat that goes out will actually deliver more output than the conventional system without heat recovery. Now we will just compare two scenarios. Scenario number one, we have a building which has a total power requirement of 2 megawatt, wherein as you can see, a major portion, around 35% of the power consumption we are assuming is to cater to the electrical chiller, and rest is for the other utilities like lighting, or maybe for lighting and for powering the computers, etc. Now if we are only dependent upon the grid, the building should have a connected load of minimum 2 megawatt. And let's say the cooling requirement for that building is approximately 1000 TR, 1075 tons of refrigeration. So vis-a-vis this, we have a system which is on CHPC. What is the kind of benefit the user has? We will try to compare. So when we represent this graphically, you have a building which has a power requirement of 2 megawatt, of which around 700 kilowatt is used to generate cooling worth 1077 TR, and the rest of the power is utilized by the other utilities. we are assuming here that the power required to drive the compressor is approximately 0.65 kilowatt per TR. So if you replace this kind of a system with a CHPC based system, what are the benefits to the user? One is the connected load of the building comes down from 2 megawatt to 1.7 megawatt, and the user can generate around 470 TR of cooling free of cost from the waste heat recovery from the engine. And the electrical chiller requirement or the dependence of electrical chiller can be significantly reduced. So the electrical chiller will cater to around 65% of the total cooling, whereas the remaining 35% of cooling will be coming from the waste heat recovery. So this absorption chiller running on the engine waste heat recovery can be serving as the base load for meeting the cooling demand, whereas the electrical chiller can come into picture when we are working on peak loads. So because of which you can see here in the new scenario, the overall installed capacity is lower. We are running an engine to cater to the power requirement of the building, and we are generating cooling free of cost. And we are reducing the size of the electrical chiller as well as the power required by the electrical chiller. So these are the total savings for the user: 300 kilowatt of savings in power and 40% reduction in the dependency on electrical chiller. Now, this is what a typical CHPC system consists of. You have a gas engine. As I mentioned, there is a exhaust gas coming out of the gas engine. Then there is a jacket water also coming out of the jacket water circuit of the gas engine. So these two are fed into an absorption chiller. And in case the engine is in off condition or not in working condition, if it is under maintenance, we can still cater to the cooling requirement by directly firing natural gas inside the chiller. So this equipment can be designed as a chiller or a chiller heater, which can deliver, let's say, cooling in summers and heating in winters. So it is purely up to the requirement of the user. We can customize this and we can have different solutions possible. Quiz time.
Yes. Thank you so much, Mr. Vaidyanathan. This was very clear and excellent technical presentation. Let's see if everyone has followed through all that you have been talking about so far. So we're going to do a short quiz, and the question will come up on your screen, and you will be able to click on the right answer that you think it is. Okay, so here is the first question. What is the typical refrigerant used in a VAM, right? That's what we're talking about, vapor absorption machines or chillers. So please select one of the options: HFC, brine, salt water, or lithium bromide. All right, so answers are coming in. Let's see what the answer is. I think I can even show you the poll. Okay, so let me tell you what the answer is. Most of you have said, 78% have said lithium bromide, and 12% said HFC, and 5 brine, and 5 salt water. So maybe, Mr. Vaidyanathan, you could just explain this. Most of them are saying 78% lithium bromide. Actually, is that the refrigerant?
Deepa, maybe I think the question is about what is the refrigerant used in VAM. So the refrigerant actually is used in VAM is water.
Water, yes. It's
Water.
not salt water, it's
yeah,
water.
And lithium bromide is the absorbent or the other solution which is used to run this absorption cycle.
That's absolutely right. So salt water is a mistake over there, but it's water. So water is the refrigerant, lithium bromide is the absorbent. And I think you also mentioned ammonia as another combination, right?
Yeah. Yes.
Ammonia and what goes with it?
Water.
Ammonia and water, right? Even in that case, water is the refrigerant and ammonia is the absorber.
No, it's the other way around. In case of ammonia refrigeration system, ammonia is the refrigerant and water is the absorbent, because water has a tendency of absorbing ammonia.
Right. Okay. So in lithium bromide and water, water is the refrigerant. Okay. Now the next question. Just 1 second. Something wrong with this. Just give me 1 second. I need to just select this. Okay. Got it. Next question up on your screen. The heat source in a van chiller is used to heat what? Do you heat water, lithium bromide solution, or both? That's the question. So you need a waste heat source or a gas or maybe steam, etc. Right? So the heat source is used for what in a van system? All right, answers are coming in, distributed all over, surprisingly. Let me show you the answer of the poll. There you go. So 50% of you are saying lithium bromide solution, 27 water, and the rest of you are saying both. So majority of you are right. The heat source is used to heat the lithium bromide solution because that's the concentrated solution, right? Is it right, Mr. Vaidyanathan?
Absolutely. It is the heat source is used to heat the lithium bromide solution.
Right, and that's what, and it returns back into its concentrated state, so that again it's ready to absorb the water vapor, and then that continues the cycle. So heat source is not used to heat the water. Water converts into vapor because there is vacuum in that particular what do you call it? Like that vessel where water is
the evaporator. Yeah.
The evaporator, yes, exactly. All right, on to our next question. So this, most of you have got it right. So that's good. Next question up on your screen is this. The heat in the lithium bromide chiller generator, right, releases what from the solution? So we spoke about the evaporator, the generator, the absorber, and the condenser. These are the 4 parts in a VAM system. So in the generator section, what happens? What releases from the lithium bromide solution? Is it the refrigerant vapor, absorbent vapor, water, or none of them? Okay, most of the answers are coming in. I'm going to stop the poll. I'm going to share the answers with you. 63% of you are saying refrigerant vapors, and that is the right answer because refrigerant here is water. And in the generator, you are actually heating the solution, and that separates the water from the lithium bromide, and the water vapor is generated. So that is the refrigerant vapor. In other words, it's the water vapor. So it's not water in the liquid form, which happens in the condenser, and it's not absorbent vapors as well in the generator. And so the right answer, majority of you have got the right answer. And now coming up, the last question. This is also pretty easy. The COP of VAM it's not COP, it's COP of VAM ranges at which numbers rather? Is it around less than 1, less than 2, less than 5 or 8? Meaning this is the maximum that it can get. This is the maximum range we're talking about. Okay, so most of you have voted. I will stop the poll right now so we can quickly see the answers and move on to the next set of presentation. Okay, so most of you said less than 2. That is the right answer. So it's still 1.8, right, Vaidyanathan?
Yes, it is.
Up to 1.8?
Yeah, that's absolutely right.
Right. And the electric chillers could go up to 7 or 8 or something.
Yeah, it is a typical range of 5 to 6. That is for the electrical chillers.
Right. And as you said, it's while the COP equipment to equipment may compare less when you compare VAM to the electrical chiller, but connected load is much significantly lower for a VAM. And you mentioned also that overall system efficiency is also greater for a VAM.
Absolutely.
Is that right? That's how it is.
Yeah,
okay.
Absolutely right.
Right. So great. I think except for one question, which was a little confusing because of the salt water. Otherwise, I'm sure everyone would have got it right. Other than that, everything else is spot on. So let's continue with the rest of the presentation.
Thank you, Diba. So moving on, in a typical CHP system, what are different possibilities with absorption technology? So we can have an exhaust which only recovers heat from the exhaust gases. So that is a very simple system. Or you can have only the hot water driven absorption chiller where we are recovering only the jacket water and not the exhaust gas. So this is the simplest of the solutions available. Second option can be an exhaust gas driven chiller heater, which means that it will recover heat from the exhaust gases and it will deliver cooling in summer and heating in winter. And in this, we have two possibilities when there are different types of heating systems, some requiring lesser temperatures and some requiring higher temperatures. So both are possible with the absorption systems. We can deliver hot water at 60 degrees Celsius or even 80 or 90 degrees Celsius. So that is also possible with absorption chiller. The third the important possibility is having a backup source. Like we have when we have a grid power, we have a backup in the form of a diesel genset or a gas genset. Similarly, when we are recovering heat from the exhaust gases, there may be scenarios wherein one may require some kind of a backup or a redundancy possibility, which can be built into the system, that in the absence of the exhaust gases, can we still make the system running? And that possibility is very much available, wherein we can have a natural gas driven backup system, which is built onto the chiller itself, which will take care of scenarios of engine outage.
Just a quick note to everyone, all the attendees, if you have any questions, please start sending it in the chat box so we can start taking them one by one, and that will be very time efficient towards the end of the webinar.
Yeah, so CHP system can be worked out in various forms. It can be with a gas engine, it can be with a gas turbine, or it can be with a micro turbine, or it can be with a gas turbine and a steam turbine together in a combined cycle kind of power plant. So there are different possibilities. The simplest of this is a micro turbine or a gas engine, which are easy and cost effective when it comes to CHP systems. Yeah, so moving on to the single effect hot water chiller, where we have absorption chillers available for capacities ranging from it is actually 18 TR, not 180 TR, 18 TR to 1650 TR. So, very small capacity chillers to very large capacity chillers all are available with hot water as the source. And this hot water can come from engine jacket water, it can come from solar panels, it can come from various other forms of heat recovery. So this is roughly how the absorption chiller cycle looks like. We don't have time to dwell more into this, but this is the cycle diagram, wherein you can see the hot water is the circuit which heats up the lithium bromide on the top side of the diagram. And so we have three systems predominantly. There is a chilled water system, there is a cooling water system, and there is a hot water system, wherein the hot water is coming from one of the sources mentioned earlier. The second form is the direct fired absorption chiller, which can directly fire natural gas or diesel or variety of fuels like LPG, town gas or biogas, etc. And capacities available are from 50 tons of refrigeration to 3500 TR, and they have a COP of 1.5. And these are one of the most preferred forms of cooling solutions in the Western world, where direct fired absorption chillers are found in most of the commercial establishments, be it a hotel, a hospital, or it can be a shopping mall, or it can be a banquet hall, etc. So as you can see in this cycle diagram, there is this generator on the right hand side, where we will be firing the fuel, and the heat from the fuel is directly transferred into the lithium bromide solution to heat it, so that we can concentrate the solution to perform the required absorption process. This is the third variety of absorption chiller, which is nothing but the exhaust gas driven absorption chiller, wherein we can have the exhaust gases coming from a gas engine or a diesel engine, or from a gas turbine, a micro turbine, from fuel cells, or if it is in an industry, it can be in variety of forms like furnaces, ovens, thermic fluid heaters, etc. The capacity range available is from 50 tons of refrigeration to 3500 tons of refrigeration. And the temperature of flue gas can be, or the exhaust gas can be, varying from 250 degrees Celsius to 600 degrees Celsius. So as you can see in this cycle diagram, we are using the exhaust gases to heat the lithium bromide in this generator, where it heats the lithium bromide solution to a higher concentration. And this is nothing but a multi-energy absorption chiller, which is a combination of any of the heat sources mentioned earlier, 100 TR. So here you can see a multi-energy chiller, where we are using both the exhaust gases as well as the hot water coming from the engine into a single chiller. So the one common part which is applicable to all the earlier types of chillers as well is that there are very small pumps which are mounted on the chiller, which require electricity. So when you compare to an electrical chiller, these pumps will be 1/10 or maybe 1/20th of the size of a electrical chiller motor. So the power consumption of these motors will be very, very less compared to an electrical chiller. And because of this, the chillers are very silent in operation and do not result in any vibration, which are of concern when you go for a commercial establishment, the noise and the vibration. So this is to talk about our experience globally, wherein we have worked with a number of engine and turbine manufacturers, where we have done the heat recovery, which is resulting in cooling and heating. So these are some of our prominent references, and we will dwell more upon the references which are in India. So DEENANATH Mangeshkar Hospital is a hospital in Pune, It is a 800 bed hospital wherein we have 3 numbers of absorption chillers of 350 tons of refrigeration each, which are driven by the exhaust gas and hot water coming from engines. So there are 3 engines, 2 working and 1 standby, and the engines cater to the total power requirement of the hospital complex, and the chillers take care of the cooling requirement of the hospital. So this installation has been in operations for the last 6 years, and they are able to save a lot in terms of the electricity cost, as well as they have become maybe kind of they have reduced their CO2 footprint drastically. Similarly, we have various references from overseas as well as in India, where we have hospitals in various other geographies which have similar kind of setup. Either it's a exhaust gas heat recovery or a direct firing catering to the hospital application. And in terms of commercial complexes, one of the prominent installations where absorption chillers maybe have been there since last 15-20 years is the American Embassy in Delhi, where we have 3 chillers totaling 1000 TR, close to 1000 TR, all running on direct firing. So these are catering to the air conditioning requirements of the embassy complex. Similar to the American Embassy, there is an American Embassy school again in New Delhi, where the air conditioning is done by the heat recovery from the engine exhaust gas and jacket water. So, we have 2 chillers, 740 TR and 425 TR, which are working on the heat recovery on 3.5 megawatt gas engines, and they have the backup firing capability to take care of engine off condition. Another important example is the GAIL Jubilee Tower located in Noida. So this entire complex goes on a CHP model, wherein they have 2 800 kilowatt gas engines, and the gas engine exhaust and jacket water is routed through an absorption chiller, which is catering to a majority of the cooling requirement of the building, and the rest is catered to by electrical chillers. This is the INFOSYS building in Chennai. Maybe a couple of years back, when there was a severe power shortage in Chennai, INFOSYS was running diesel engines for catering to the power requirement of the office complex. And they had taken the heat recovery based solution from Thermax for recovering heat from the gas engine, diesel engine exhaust, and generating hot water to run absorption chiller, which was catering to a large portion of their cooling demand. GRANDE HYATT in Mumbai, one of the earliest users of absorption chillers. They had a 800 TR absorption chiller, which was catering to the cooling requirement, and it was of direct fire type. Similarly, another hotel in south of India, which has absorption chillers catering to the cooling requirement. So as you can see, most of the commercial complexes, they have this requirement, and the cooling requirement can be met efficiently using an absorption chiller, either through the CHPP mode, where you have the engine heat recovery, or it can be through direct firing of the fuel. So I'll just glance through some of these references, maybe the BBC studios or the Paramount Pictures, or maybe there are certain prominent complexes in Turkey or Australia. Most of the, as you can see, across these geography, one common part is that most of these people have gone for environment friendly solution for meeting their power and cooling requirement through CHP. Because unlike the coal-based power plant, the gas-based power plant emit a cleaner form of exhaust gas, which can also help to bring down the pollution levels in our cities, which are now today choked with particulate matter, PM 2.5. Every day you read in your newspaper that there is maybe a lot of pollution happening, and people are getting affected because of that. That can be reduced to a large extent by going for a more environment-friendly solution. So California State University, Fullerton in LA, different universities across the USA and some in China, which have also adopted this kind of a solution. Airports, maybe big establishments which require round-the-clock cooling and round-the-clock power. So they also adopt the CHPC for meeting their cooling and heating requirements. Data centers. Data centers are one of the emerging sectors. So they require redundant and reliable power round the clock, and moreover, since they are dealing with high-end computers, they require a lot of cooling to keep these servers across the running across the globe. So they are also adopting CHPC as a proven technique for achieving these requirements. So we have come to the end of this presentation. So now we are open to any questions.
Right. Yes, without further ado, I jump right into the questions because we have a lot of questions here. The first question is, does the COP of VAM chiller include energy consumption of pumps?
Yes, it is including the pumps, because as I mentioned, the pump power consumption is negligible when compared to the heat that it takes. But even if you exclude that, it doesn't change the figure by not more than the second or the third decimal point.
Right. Next question, is there a cost to sustaining the vacuum in the evaporator?
No, the vacuum inside the machine is sustained by the absorption process. What we do is that we make these vessels hermetic. That means that they are leak tight, and they pass through certain special testing processes like the helium leak test to ensure that this vessels remain hermetic throughout the life, which is 20 to 25 years. So it can remain leak tight for the entire duration. So there is no special equipment required to run continuously to maintain this vacuum.
Okay. Next question, what could be payback if a screw chiller of 100 tons capacity is replaced by the same capacity of a VAM chiller?
So the payback is nothing but a financial calculation. So it depends upon the cost of electricity and the cost of the heat source. If I mention that the heat source is waste heat, like the jacket water or the exhaust gas or some kind of form of vapor or something, the payback can be as low as 6 months, and it can maybe as high as maybe 2 to 2.5 years. So it depends on case to case. But wherever there is a waste heat recovery related cooling solution, it will be less than a year.
Right. Next question. Does the quantity of the lithium bromide solution depend on the cooling capacity of the system?
Yes. The size of the equipment, the quantity of the absorbent and the refrigerant, that is the lithium bromide solution and the refrigerant DM water, depends on the size of the equipment. Larger the capacity of the chiller, more will be the quantity of absorbent and refrigerant required.
Okay. Next question. What are the challenges other than cost for making smaller capacity VAM that are viable for domestic application?
See, the first and foremost challenge, it is not on the not in the absorption technology. The main challenge is making the heat source available and the cost of the heat source to be cheap enough to be used for domestic applications. Second is the size of the components, like the control systems, the pumps, etc. If there is a demand, yes, this also miniaturization can be done. since the demand from the domestic sector for individual air conditioning units is not there, development has not happened in that direction. That is actually keep making the cost higher. But there is a possibility of scaling these down. Having said that, what is more important is to look at a district cooling kind of a solution rather than going for a distributed cooling solution using split air conditioners or smaller absorption chillers. Why? Because there will be always economies of scale which will come into picture when you go for a centralized system.
Sorry, I think you couldn't hear my question. The next question is actually related to that district cooling. The question is it economic to connect VAM to district cooling network in the summer to produce cooling?
Yeah, absolutely right. See, there has been a lot of movement happening in this direction because of the fact that now we are talking about smart cities. So when you have such large cities coming up, there is obviously going to be a spike in the cooling demand, and as the affluence of human beings increase, the demand for cooling is bound to rise. Now, having said that, if you are to if you are to go for individual or maybe smaller cooling solution like the split air conditioners or the VRF systems, etc., for the individual houses, what would happen is that again you will be challenged in the form of increase in electricity requirement, so on and so forth. Coming to absorption chillers, the most important part is that we can go for a centralized model wherein waste incineration can generate the maybe driving source for the absorption unit in the form of steam or exhaust gas. And such large absorption chillers can run round the clock and generate cooling, and this can be distributed very efficiently using underground pipes to the individual users and individual buildings, and generate a sustainable model for green cooling. See, similar systems are adopted in the district heating mechanism. If you look at countries like Denmark and Germany, they run absorption heat pumps to generate heating, which again from a district heating plant will be supplied to individual users. And this has been this model has been in existence for the last 30 years. And the year over year they are increasing the capacity or installed capacity of such absorption heat pumps. Also, a similar solution is very much possible in the absorption cooling field as well, wherein a centralized system can be more efficient and be more sustainable as well.
That's a great point. That brings us to the next question. You were able to achieve 300 kilowatts of savings of connected load by using an absorption chiller plus a heat generator. Was there a whole life cycle study like a CapEx versus OpEx done for this?
Yes, this is a very well established model. Okay, the capex, as I mentioned, the capex will be definitely higher, but the payback is tremendous. We have to bear in mind is that the electricity that we use today is highly subsidized. The moment the subsidy is reduced, the moment the cost of electricity goes up, this is going to be having a much faster payback. And it is going to be easy for the governments also going forward, where they don't need to invest in large power plants. They can simply supply the gas and let the users install and run their own power plants. So this model is already existent in the West. Many countries have started moving towards the CHPP systems. So the model is well established and the paybacks are well quantified.
Correct. And now come to the last question. What is the cost per ton for a VAM system?
See, the cost per ton of VAM system depends upon the size. See, like unlike the split air conditioners or maybe the electrical units, the larger the size of absorption chiller, the most cost effective it would be. So having said that, since we are talking about different variety of absorption chillers, I can give a rough rule of thumb. Maybe something like a 100 TR absorption chiller can cost you anything between maybe 25 to 35 lakhs, whereas a 1000 TR absorption chiller may cost you maybe something like 2 crores to 2.5 crores. So as you go larger and larger on the scale, the cost per TR comes down drastically. I'm just giving you some ballpark numbers. The exact numbers we can discuss on a case-to-case basis.
Right. That was the last question, and thank you so much. Thank you so much for taking all the questions, for a clear and to the point explanation of the technology, and also in responding to all your questions. I thank you so much for taking our time and sharing our knowledge on this webinar. And before we end the session, we have a few announcements to make. 2 weeks from now, on 29th, we have the next session on renewable energy market scenarios and policy framework by Dhruv Ballal from CII. Do tune in for that one. We have 2 NZEB tours coming up in Hyderabad on 22nd November to the CII Green Business Center, and 23rd November at INFOSYS INFOSYS campus at Hyderabad as well. CII is a net zero retrofit building, and INFOSYS is a net zero campus. What you call, on a campus scale, it is a net zero project. So both are on a different scale and various things that you could see, which is extremely insightful. The tours are free. Please register on our website or on social media. You can also subscribe to our monthly newsletter, the NZEB Times, to get all the information about our efforts in driving engagements for NZEBs in India. And if you haven't yet visited our website, please do so today at www.nzeb.in. It has all the resources regarding NZEB, including case studies, the webinar recordings, the webinar summaries, blog, and all the latest events about NZEB. Do connect with us on social media if you want live updates about our initiatives. And here is the YouTube channel that we have. All the webinar recordings can be accessed on the public domain on the NZEB India YouTube channel. So you may access the recording of previous webinars as well. With that, thank you so much for your time and your interest in listening into this webinar. I will see you on the 29th.